Hello everyone. In this video, we are going to start a new chapter that is known as the flexure member or the beams. And the first topic will be the cross sections which can be used as beams. So let's start. So as we study in the case of the structural analysis that the beams are the member or the structural members which are subjected to transverse loads. That means the load which will be perpendicular to their longitudinal axes. So the beams are subjected to transverse load which causes the shear and bending moment in the case of the beam. And as we know the anatomy of the structure, so the topmost member is the slab, then the load is transferred from the slab to the beams. That means any load which will be in the superstructure that will be transferred to the substructure with the help of the beams. Then beams transfer these loads to the columns and then columns transfer these loads to the footings. So this is the basic load transfer mechanism which acts in any structure. That's why the beams are an important component of the structure, and that's why the designing of the beams is very important. So let's say this is a three-dimensional view of the beam. If we look at this section which is present at the mid portion of the beam, so if we look at this portion, then under the compressive loads, that means if these are the loads which are present on this beam section, then under these loads the topmost member the topmost member will be subjected to compression while the bottommost part which will be subjected to tension. And as you can see, the middle portion which is known as the neutral axis portion or the neutral axis plane, because it is a three-dimensional diagram. So this neutral axis is not experiencing any kind of stress. That's why it is neutral, and that's why the name comes as the neutral axis. So the loads perpendicular to the longitudinal axis of the beam, that is known as the or the so the load coming perpendicular to the longitudinal axis of any structural member is known as the beams. Now usually when we design for the RCC structure, so in that we have seen that any RCC structure we provide the beams in form of a rectangular member, and because of that there is suitable width and depth which is provided for the RCC beams. And that's why the major type of failure which occurs in case of RCC structure, that is because of the shear failure or bending failure or the deflection failure. These are the primary criteria in which the RCC member or RCC beam fails. But in case of steel structure, usually we provide the section in the form of I sections, and these are having very low thicknesses. That means the value of the thicknesses either of the flange or of the web, they are very less, because of which the other type of failure in addition to these three occurs, which is known as the buckling failure. And this buckling failure may be of two types. It may be the lateral buckling, that means the buckling of the whole system as a one, while it may be a local buckling, that means the buckling of individual components of the section. Now to avoid this, what we need to provide, we must have the symmetry in the structure. So to have the symmetry, we are having different sections. So let's say this is the one section that we are having. So in this we can see that this is one plane of symmetry and this is the another plane of symmetry. Therefore in this type of connections the only simple bending will occur, in which the load is symmetrical or it is being applied to the plane of symmetry. Now if the loads are having only one axis of symmetry, that is in this case, in a case of channel section, we see here that in these cases we will be having a biaxial bending depending upon the position of the load, or there may be movement along with, that means this is a bending moment along with the torsion because of the centricity changes. While in case of the angle section, so as in the case of angle section, there is no axis of symmetry except the one about its shear center. So if the load is being applied at the shear center, then it is okay. If not, then the member will be experiencing a different type of bending, which is known as the unsymmetrical bending. Therefore, in the case of the steel structure, we will be restricting our discussion to the simple bending type of steel sections. So that means majorly we will be choosing the sections which will be having at least one axis of symmetry, or at the most it will be having two axes of symmetry. So depending upon the uses or the place of use in case of buildings, the beams are classified into different types, which are, so these beams are classified as joist if they are closely spaced beams supporting the floors or the roofs of the building, but they are not supporting the other beams. That means, so joists are the closely spaced beams supporting the floors. That means if we are providing these, let's say these are the joists which are provided, then on top of it only the floor material or the floor covering will be provided so as to support them, but they will not be supporting other beams. Now the girder, which is used for supporting the number of joists, that is known as the girder. So a beam which is used for supporting the number of joists, that is known as the girder. While if we are using the beams to carry the roof loads, then that type of beams are known as the purlin. And to support the purlin, the type of beam which are provided, that is known as the rafter. Now in case of stringer beams, so whenever we are having a residential building, so the beams which are provided at the periphery, they are known as the stringer beams. Then the next type of beam is the floor beam. As the name itself says that this is the beam which is supporting other beams in the building, or majorly they are supporting the transverse beams provided in case of the flooring. Now it will be clearer from this image. So the joists are the beams which are provided to support the floor. So on top of this joist member, we will be providing the floor covering. And the beams which will be supporting these joists, those are known as the girder. So the beams supporting them, they will be known as the girder. Similarly, in case of the pitched roof truss, we can see that the purlins are the members. So in case of the pitched roof truss, we can see that these are the inclined members on which the roof material, usually the GI sheets or other type of sheet which is used as the roof covering material, they are provided on top of it. So these material which transfer the load from the roof covering to the other members, they are known as the rafter, and the rafter are supported on the purlins. So that means the ultimate load will be transferred from the roof covering to the purlins, and in turn the roof is supported with the help of the joist, and these joists are supported by the help of the girders. So this is the mechanism. Now other type of beams are the spindle beams. So spindle beams is a beam on the outside perimeter of the floor. So as we have seen that there are two types of beams, spindle beam and the stringer beam. So stringer beams are provided whenever you might have seen the staircase. So a staircase is supported on a beam. So that beam is known as the stringer beam, while the spindle beam, it is a beam which is on the outside perimeter of a floor, supporting the exterior walls and the outside edge of the floor. While this type of beam, that is known as the girt, it is a horizontal beam spanning the wall columns. That means it is provided in case of the industrial buildings. So that is the important classification, and from column to column they are running. So in this manner, the beams will be running from column to column. A rafter, as we have seen, that it is a beam supporting or supported by the purlins. And lintels, these are the beams which are provided above the openings. So whenever we are designing the construction, so whenever we are designing a building, so over the openings that are provided in case of any building, and usually we design the buildings with the help of the masonry work. So the beams which are provided over the masonry work over the openings, that those are known as the lintels. Those are known as the lintels. Now everything will be clear from this image. Now these are the beams which are provided on the periphery. So these are the beams which are provided on the periphery, while these beams which are supporting them or resting over them, they are known as the secondary beams. So these primary beams which are provided on the periphery, these are known as the spindle beam. While this type of beam which is provided here over the opening, so this is an opening for either for the door or for the window, then the beam which is provided over the opening, that is known as the lintel. So this is the lintel opening and the beam is known as the lintel. Now another type of structure may be a industrial building. Now in this industrial building, between the wall columns, these are the wall columns, the beams which are running from column to column, they are known as the wall gird. While the member which is supporting the rafter, they are known as the roof purlin. And on roof purlin, these members which are supporting or carrying the load from the roof panel or from the roof covering, they are known as the rafters, and rafters are supported on the purlins. So these are the different types of beams depending upon the place of use. Now what is the nature of forces acting on the beams? So whenever we design a beam, it is assumed that the beam is subjected to only transverse loading. So because of the maintenance of the symmetry in the structure, what we assume that the beam is subjected to only the transverse loading, and that's why it will be causing only the bending. And as we know the from the pure bending equation that we have studied in the strength of material, so the pure bending equation says that m upon I is equal to F upon Y is equal to E by R. Now from here, if we check that this m is proportional to I, because m can be written in the form of F into I by Y, or this stress is inversely proportional to the moment of inertia. So what we try to do or what we try to achieve in case of the design of the beams, we try to increase this moment of inertia so as to increase the moment capacity and to decrease the stresses in the beams. By increasing the moment of inertia, both the objectives are achieved. That's why we try to provide the section in such a way that the most of the material is shifted on the outskirts of the member on the section, such that the moment of inertia increases up to a such quantity, so that the moment carrying capacity and the stress moment carrying capacity increases and the stresses they get reduced. Now this beam may be subjected to, I've told you that this beam may be subjected to either simple bending or unsymmetrical bending. So a beam may be subjected to these kind of bendings. I've told you the simple bending or an unsymmetrical bending or the biaxial bending. Usually we do not take into account of the biaxial bending because it is an advanced course. Then unsymmetrical bendings are avoided to avoid the torsion phenomena, because for torsion we do not have simply the equations to solve them, and it is a complex phenomenon. Now for simple bending to occur, the load must pass through the plane of symmetry, or in case of the unsymmetrical section, the load must pass through the shear center so as to avoid eccentricity. Now to avoid eccentricity, we are providing the load through the shear center. So this is the shear center at which if we apply the load, there will be no torsion. But it may not be possible to completely avoid the torsion, and that is because whenever we are providing the ice or any other rolled steel section used as a beam, so we know that the under the transverse load the beam acts in this manner. That means the top portion is in compression while the bottom portion is under tension. So under the heavy compressive load at the top portion, there may be a buckling criteria. And this buckling criteria is generated because of the torsional stresses, which are because of the extreme compressive stresses. Now this buckling can be lateral buckling or it may be a local buckling. So that's why the torsional equation is not completely eliminated even if we are providing the symmetrical sections. So this buckling, it depends upon the width to thickness ratio. That means if we increase the thickness, that means we are compacting the section, so this buckling will decrease. Or if we are decreasing the width of the section, then also we can reduce the buckling. So these are the two possibilities with the help of which we can control the buckling phenomena. Now, what are the different types of steel rolled sections which can be used as the beam? So, the types of steel sections which can be used as beams. So, primarily we classify the steel sections which can be used as beams as the rolled steel sections. So, these are the steel sections which are readily available in the market depending upon our specification. That means if you ask in the market that you require a solid section of the steel member having certain diameter, then you will be readily available with that material. Similarly, for the channel section or the rolled eye section or fabricated eye section, these are the type of sections which are readily available in the market. Then the next type of section which can be used after rolled steel sections are known as the built-up sections. Now, as the name says itself, that whenever we are not able to achieve the required strength or required criteria with the help of these rolled steel sections, in those cases we construct the steel section ourselves with the help of the plate members. So the thin walled closed section, or which is also known as the box section or fabricated eye section, these fall under the category of the built up section so as to achieve the required criteria. Then the next type of section which can be used, that is known as the compound section. So whenever we are using more than one rolled steel section in one beam, for example in this we are using an eye section as well as a channel section, so as to increase the compactness in the compression side. So that type of section used as a beam is known as the compound section or compound beams. Next type of beam which can be used, that is known as the composite beams. So these composite beams are provided whenever we want to increase the compactness at the compression side. So in this we are using two different material, that is concrete and as well as the steel. So the composition of these two is known as the composite beams. Now the next type of beam which can be used as the next steel section which can be used as a beam, that is the encased beams. So whenever a steel section is encased in the concrete structure, that is known as the encased beam, and if we want to increase the strength of the section, so we can use these two types of beam also, that is a tapered section or the castellated beam. So these are the two different types of sections which can be used as the steel beams if we want to achieve the increased moment carrying capacity. How will we do that? That we will see one by one. So these are the possible 7 types of steel sections which can be used as beams. So now looking at the first type of sections which can be used as a beam, those are known as the rolled steel sections. Now in the rolled steel sections, a number of sections are used for the beams. Now in this case, the prime example is the rolled eye section. This is most commonly used. The reason for the use of this eye section, so let's say this is an eye section which is used for the steel beams. So the reason for the use of this eye section is the double symmetry which is achieved when we are providing these sections, and the another reason is that for given weight, that means if we are using different cross sections of same weight, for given weight the moment of inertia for an eye section is maximum or it is higher than the other section. So that's why we try to provide an eye section, because ultimately if we increase the moment of inertia, the radius of gyration it increases, which in turn decreases the slenderness ratio, and which in turn increases the design carrying capacity of the section. So that means with the help of the I section, we can use the I sections to transfer the heavy loads. Then the another type of sections which can be used in the rolled steel section, those are the channel sections. Now channel sections are having only one axis of symmetry, which is along this axis. So these rolled channels, they are suitable for light loads only, because they are having only the one line of symmetry. That's why they are used only for the lighter loads. Now this single angle section or the T section, they are inherently weak in bending. That means whenever we want to provide the load through them, they are not having the symmetrical axes. So what will happen? There are prominent chances of the bending which will be occurring in these sections, or the case may be that there may be a torsion scenario. So that's why we try to avoid these type of sections. So there are different limitations of using these angles and channel sections. So limitations of T sections and angle sections to be used as the beam. So these sections, they are inherently, that means they are primarily known as, for this criteria, they are inherently weak in bending. Then the next criteria, now this is the first limitation of the T section and the angle section, that these sections are inherently weak in bending. That's why they cannot be used for the transfer of the bending moment. While the beam section which we are designing, we have seen that for a simply supported beam, whenever we want to design it, so they are bending moment and the shear force which will be acting. So the bending moment and the shear force, these are the prime criteria in which the beam has to resist the loads. That's why these T section or the angle sections, they are not used because they are weak in bending. And they are used at the places where they can be executed satisfactorily, or they can be performing satisfactorily. So they are used at places of satisfactory execution. That means the places where already the constructions has been done with the help of these kind of sections. Now since the load is not in the plane for these sections, so there are chances of the torsion. And for these type of section, we do not have the equation or the capacity to calculate the torsional capacity. So it is complicated or complex to calculate. So it is complex, or it is complicated to calculate the lateral buckling criteria or the lateral buckling phenomena in case of the T sections or the angle sections. So that's why we usually avoid these type of sections to use as the beam. So usually the most efficient section is the I section, which can be used under the rolled steel section. Now this I section can be provided in the form of the rolled steel section or in the form of the built-up section. So the second criteria which we use for the beam member, that is known as the built-up section. Now this built-up section is usually provided in case of the bridges with the help of the I section. So this is the plate girder. That means, let's say if this is the capacity of the I section, this is the rolled I section that is available in the market readily. Now the thickness which I am requiring for the construction, if the web thickness is not suitably achieved, then what we can do, we can construct the I section with the help of the different plates. So let's say this is one plate, and this is another plate, and this is the another plate. Now with the help of these I sections, with the help of these plates, we can weld these plates at these points so as to obtain the required shape of the I section. And the thicknesses of the plates, they will be selected by us, so we will be getting a suitable I section, and the section is known as the built up section because it has been built by us. and usually this type of section is known as the plate girder. If it is a closed section, that means if we are closing this section from both the sides, then that is known as the box girder, or if it is having a lesser thickness, then that is known as the box column, or simply that can be known as the plate girder as the three plate column. Now, to increase the stiffness of the compression side, what we can do, we can provide this plate girder with some cover plates so as to increase the moment of inertia. So from the neutral axis, the mass of the maximum material is shifted outwards, which will be increasing the moment of inertia, which in turn will be increasing the moment carrying capacity and will be reducing the stresses coming onto the section. So that is the use of the built-up sections, which is primarily seen in the case of the bridges. So you might have seen these kind of box sections which are used in the case of the bridges. Now, third type of section which can be used as the beam, that is known as the compound beam. So compound beam is used whenever it is made up of two rolled sections. That means either we can be using I section or the channel section, or I section or the angle section, or I section and the T section. So these are the different type of combination for the compound beam, or simply we can be using a plate over the I section so as to strengthen the compression side of the I section. So as we know that under the compressive load, the beam show this type of stress diagram, that is top portion is under compression while the bottom portion is under tension, and steel is inherently good in resisting the tension. So to strengthen the compression side of the steel, what we do, we provide additional material at the top. So this is provided to compound sections are provided to provide sufficient strength to the compression flange of the I section. So this is the important criteria for the compound beams. Now the next type of beam, that is the fourth one, those are known as the composite beams. Now in case of the composite beams, as the name says, that it is composed of the two materials. So whenever we are using two members, that is a concrete and the steel, for the construction of a beam of to carrying out the load, so that type of member is known as the composite beam. Now in this section, this I section has been provided at the bottom, which is a steel section, while a concrete section has been provided at the top. So this is provided so as to achieve the required criteria. That means to resist the tension, we are providing the steel at the bottom, while to resist the concrete compression, we are providing the concrete at the top. And to achieve the better connection, we are providing these shear connectors so that there is no lateral movement of the I section or the concrete section with respect to each other. Or other criteria may be that we may stiffen this I section by providing this complete section under the encased beam. So this composite beam is also used to strengthen the compression flange of the I section. Now next type of beam is known as the castellated beams. Now what happens in this castellated beams? So we have studied that from the equation of pure bending, we know that this is M is equals to F upon Y into I. So if we increase this moment of inertia, we will be increasing the moment carrying capacity. And this moment of inertia will be achieved in the higher terms whenever we want to achieve the maximum material at the periphery of the section. So for that, what we do, we provide the cuts along these beam section. So these cuts, when we are providing, the beam will be lifted up by this amount. So that means this will be the gap which will be there. Now then, this section is shifted in the forward direction while the bottom portion is shifted in the backward direction. When we provide this kind of movement, so these flatter portion, they will be overlapping each other. Now at this point the beams are connected with the help of the welding. So these are the portion at which welding has been done. Now because of this, what is happening here, the overall thickness of this I section, it has increased significantly. Now since this thickness has increased, that means the moment of inertia has increased, because of which the radius of gyration has increased, and because of which the lambda, that was the slenderness ratio, it was decreasing, which in turn will increase the load carrying capacity, and which was the ultimate objective of using the castellated beams. And these hollow sections, these are the openings provided in the beams which reduces the weight for the given depth. That's why it is also economical for use the beams as the castellated one. Now another type of beam that can be encased beam, that means when the complete beam section, this was the I section, if it is completely encased in the concrete section, in the concrete filling, then that type of section is known as the encased beam, and this is also provided to resist the compression at the top, and to resist the tension we are providing the I section, and it is provided with more width at the top because the compression will be more at the top portion. And the last type of section which can be used, that is the tapered beam. So these tapered beams, these are provided so as to obtain the sufficient strength that we have seen in the first diagram. So as we have done in the case of the castellated beams, what we are doing here, we are providing the cut along this line. We are providing the cut along this line, and then we are moving this portion in the reverse direction. So this is rotated, and because of which this shape will be achieved. And at the joint of these two portions we are welding it. Now when we are moving along the length, the parameters, the thicknesses, they are increasing towards the end of the section. So whenever we are requiring the tapered section, we can provide the tapered section with the help of the cut in the I section. So these are the different steel sections which can be used as the beams. Now whenever we are designing the beams, we need to consider few criteria. So beams should be proportioned for the strength, because the beams are resisting the load with the help of the bending and the shear. So that's why they should be proportioned suitably so as to obtain the strength sufficient enough to resist the bending and to keep the lateral and local stability of the compression flange in check. And that's why the selected shape, whichever of the sections that we have seen we are using, they must have the capacity to withstand the essential strength in local shear and the local bearing. So they must be strong enough in bending as well as in the shear. And the beam dimension, they should be proportioned in such a way so as to obtain the required stiffness, so that the deflection and the deformation, they are under service condition. So that means the deflection and the deformation, they should be up to a limiting extent. That means it may be possible that because of the excessive deflection or deformation the structure may not fail, but it may not be pleasing to the eyes from the aesthetic point of view. That's why under this serviceability condition the structure should be failing. So under the serviceability condition the structure may be failing, and that's why the structure, that is the beam dimension, they should be proportioned in such a way that we are achieving the required stiffness. So in the next video we will look at the different type of modes of failures for the beams. Thank you.